Now let's look at our data. There are all unprocessed fact that could be something like what you have here. So a column for a variable. So the first variable being name, Mark, Elvin, Linda, and like that. And then gender, male, female, female, like that. And age, 12, 23, like that. Now, when you have something like this, um, you could take the variables one by one. For instance, you may take the variables one by one, rather, and you may say something like gender, male, male, female, female, male, male, or you may take age, 12, 23, 14, 23, 12, 23. Now, if you're taking gender, for instance, then we'll have a frequency distribution uh, by doing this. So, like a value and you check the number of times that it appears. So male appears 4 times, so the frequency is 4. The frequency is 4, and then we have male to be 4 times. Then we have female appearing 2 times, and female here, that's 2 times. Now, this will become a frequency distribution. So this will be called a frequency distribution, rather. And the kind of frequency distribution that it is what we call the categorical frequency distribution. So the nominal here is showing because actually there's no order. You can't say male is greater than female, female is greater than male. All right, so coming to age. So we can see that 12 appears 2 times, 14 appears once, and 23 appears 3 times. So each variable and the number of times it appears. And so the number of times each value and the number of times it appears. So the number of times a value shows up for a particular variable is called its frequency. So the frequency distribution for age is what we are seeing here. So it's a numerical frequency distribution because this has to do with numbers that you can arrange in ascending or descending order. All right, so we go on. So just as a small revision, types of variables, the nominal and ordinal variable are categorical variables. The interval and ratio are numerical variables. So please take note of that. It's very important. Okay. So going on. Okay. So going on. The interval and ratio, if a variable falls on the interval or ratio scale, then it's numerical. So if it is measured on that scale. All right, now, so the grouped frequency distribution. Now, assuming that we have numbers or our data is something like 9, 5, 6, and all of that till the end here, then we may decide to categorize them and count. For instance, we may say 1 to 4. So when I say 1 to 4, that means that we are saying 1, so 1 inclusive, 2, 3 inclusive, and then we have 4. So in the same way, 5 to 8 will mean start from 5 and end at 8. So we start 5, 6, 7, and finally 8. So please take note of that. And 9 to 12 follow suit. So all the numbers that fall among this, now when we count them, there are 7 in number. So look at the numbers that were cycled with a blue color, a blue marker. That should be 1, 2, 3, 4, 5, 6, 7. So they are all 7 in number. And 5 to 8 are cycled with a red marker. So if you count, you have 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the numbers from 9 to 12 are 4. So look at that now. You cycle 1, the ones in green markers, the ones cycled with green markers, 1, 2, 3, 4. All right, so that's how to do your group frequency distribution. So you have a number, okay, you have a class that consists of a set of numbers, and then you look at how many times they appear, and you count for each of the the classes. So each of the class intervals that we have here, and then you have what we call a group frequency distribution. Now going on, a group frequency distribution may be extended as you can see below. So don't forget 1 to 4 means 1, 2, 3, 4, and then 9 to 12 means 9, 10, 11, 12. Now let's look at what we call the upper class boundary and the upper class limit. So looking at the class interval, another word for the class interval is class limit. So you may have it class interval, then you may have it called class limit. So please take note of that. All right. So now for the class limit or class interval, there is the upper class. Let's use the word limit now for this time around. Now lower class limit is always the one at the left when you look at the class interval, while the upper class limit is always the one at the right. So you can see that from the diagram shown, or rather the arrows that are drawn to it. Then you attach to them. So then when you look at the lower class boundary, the class boundary is obtained by removing 0.5 from the lower class limit. So you have 0.5 here for this class. Then you add 0.5 to the upper class limit. That gives you 4.5. So if you do the same thing for this, remove 0.5 from here, you have 4.5. Add 4.5, add 0.5 rather. Okay, remove 0.5 from 5, you get 4.5. Add 0.5 to 8, you get 8.5. Remove 0.5 from 9, you get 8.5. Add 0.5 to 12, you get 12.5. So if we had more classes, we would have continued with the same thing and we're going to have a result. And looking at this, you have, okay, the class width that you're going to say 4.5 minus 0.5, and that's going to give you 4. So you do the same thing for the next one. 8.5 minus 4.5, that will give you 4. Then 12.5 minus 8.5, that will give you 4. All right, so you can see the formula below. Now, it's important for you to know that you can obtain what we call the class mid-mark or midpoint also. And that one can be done by using the upper class limit and the lower class limit. So the upper class limit plus the lower class limit. So divided by 2. Now, so if you do that, you are going to have, for the first one, you're going to have 1.1 plus 4. Okay, let's start from the upper first. That would have been 4 plus 1. 4 plus 1 divided by 2. For the next one, next class would have been 8 plus 5 divided by 2. So the first one would have given us 2.5, which you are seeing here. That would have been 5 divided by 2. The second one would have been 13 divided by 2, and that would have given us 6.5. And that's what you can see here. Okay. Okay, that would give us 6.5. This would give us 2.5. And the next one, if I had written it, okay, would have been 9 plus 12 divided by 2. And that's going to give us 21 divided by 2. And when you look at that, that's going to give you 10.5. So 10.5. And that's what you can see here. All right, so the next column is the column of the frequency. So we go on. You can look at this. Look at this also. All right, so we go on. Now, we have done all of that, but what about if we want to determine the number of classes for a frequency distribution? Now, imagine that I have the sample 105, 106, 105, 206, and 300. And this data that we have is in such a way that there are 150 observations. So 150 observations. I've not listed everything. I've only listed 1, 2, 3, 4, 5 of them. But the dot here shows that there are many more. So this is just 5 of them displayed of the 150, but this dot here is telling you that there are many more values, but they will not display. And then, but supposing we have 150 of them, assuming that we even group them out all completely, then how do we determine the number of classes? Now, I did not write everything, but I'm assuming that the minimum value that we can have is 105, and the maximum value is 300. So now there are a number of ways to do them. I've written Studs rule as the first, but let's look at domain knowledge, and deciding based on what you want. So let's look at domain knowledge. Domain knowledge has to do with you knowing that particular stuff, the particular problem at hand. Okay, let's assume you're an engineer and you already have knowledge of that particular thing in the field of engineering. So it helps you in that regard. So you can make decisions on the number of class based on the knowledge you had before in engineering. So let's look at maybe, for instance, medicine or demography. If you have knowledge of that, it may really help you when you are trying to deal with things in that area. So that has to do with domain knowledge. Now you can decide based on what you want. You look at it and say, okay, let me just have 5 classes. Let me just have 6 classes. But this is more or less the most archaic way of doing it, or rather a primitive way of doing it, and may introduce a lot of bias. Some other persons might have worked on this in your own domain of knowledge, and so you may just use the person's own. But when you decide based on what you just feel like, what you just want, it may be wrong. So, but there's an advantage when you use Studs rule with domain knowledge. So, but let's look at what Studs rule is. Studs rule says, okay, the number of classes should be equal to 1 plus 3.322 log n. And so what is n? N is the number of observations that you have. So you just put, in this case, I told you that n should be like, let's assume it's 150. So you put that. So if you find log 150, so you multiply this out, you multiply this, you're going to get 7.229, and that will give us 8.229. But we are not approximating. We are not approximating this. We are only going to the next number after this. So whatever this is, even if it, as long as it has 8, even if it were 8.0, whatever it may be, we'll go to the next number after it, and that will be 9. So if we had 6, the next number after 6 would have been 7. So we would have gone to 7. We would have decided our answer is 7. Please take note of that. We are not approximating, but we are actually saying, oh no, the next number after whatever we obtain here. All right. If you use Studs rule, you may need domain knowledge, as it may be, the case may be. Domain knowledge may be also helpful. How? Because you may have a class that may be perhaps too large, or maybe somewhat. You may have a class that may not really be reasonable. Sometimes number of class that you have here, that may not be reasonable. So domain knowledge may help you to actually reach some compromise, or help regulate what you obtain from here. So as a general rule, Studs rule is important, but domain knowledge also can help you. All right, so randomly, let's look at determining the class width. Now, after knowing the number of class, you may want to know how many numbers should be here. So the other time we did 1 to 4, I told you numbers involved would have been 1, 2, 3, and 4. Now, so in that case, yes, the width was going to be 4. So how do you get the width? One way you could do that, or one way you can do that, is by saying I talked about that just earlier. Okay, so you may do upper class boundary minus lower class boundary, and that gives you 4. But you could also say upper class limit minus lower class limit plus 1. So, and that's what I'm going to be doing here. So please look at this. Whenever you say you have a number from 1 to 4, there are actually going to be 4 numbers here. Why? Because if you do 4 minus 1, you're going to do plus 1. That will be the total numbers that you have from 1 to 4. So that means you are counting the first number. The first number is included. So So when you do this, you're going to have 3 plus 1, and that will be 4. So if the number you're talking about now, we're from like maybe say 5 to 8, then you'd have had 8 minus 5, so upper class limit minus lower class limit plus 1, and that would have given, permit me to change the marker color here so you can follow, and that would have given 8 minus 5 would have been 3 plus 1, and that would have been equal to 4 also. Now, so if you check the numbers involved, they will be 5, 6, 7. So you would have had 5, 6, 7, and 8. And so as you go on, you'll find out that you have 68 numbers in this class, 16 numbers in this class, and 10 in this class. And so the class width, we have unequal class width for each of the classes except for the first 2 classes, which are equal. So that's not good for us. Actually, that's not good for our work. All right, now we could actually use a better way or better method, and what would that be? We may decide to set the class width. Instead of doing that on our own, just randomly selecting your own class width, we could say, okay, let the class width be the range divided by the number of classes. So range is equal to the maximum minus the minimum number of observation. Range is equal to the maximum observation minus the minimum observation. And the number of classes we know is already 9. So the maximum, as I said before, I said I'm assuming that the maximum is 300. So if you remember that, 300, and the minimum is 105. Now, so when we do that, we are going to have the range to be 300 minus 105, and that will give us 195. And then the class width, being the range divided by the number of classes, will give us 195 divided by 9. All right, so, and that is going to give us 21.667, but we are not approximating this. So whatever you have here, you go to the next number after it, and that is going to be 22. So the next number after 20, whatever you have, 21 here or whatever you have here, is the number you're going to write. You're not approximating. So if you have 21.0, whatever you have there, you are going to write 22. Not even, because you know 21.0, for instance, maybe 6 or 1 or something, should have been approximated to 21, but you're going to write 22 still. All right, now, so hence the data can be put in tabular form this way. Now, all right, for those of you who are very inquisitive, you would have noticed that the column here changed, the one in red. I just needed to, okay, I had to adjust some of that, I have to adjust some of the things you have here. All right, look at this now. So now we have decided that our class width should be 22. So what do we do? First of all, you may add, okay, you start from the smallest, or you may have something that is smaller than the smallest if you want. The reason why I had to change this was because I initially used 100 okay, as the smallest value that we had here, so which was the lower class limit of the first interval here, but I don't have to use 100. The reason why I used 100 before was that you could have the first of your, okay, the lower class limit of your first class should be less than or equal to your minimum, the minimum that you have. And don't forget that our minimum in this case is 105. But after doing it with a minimum of 100, using the lower class limit here as 100, I found out that we couldn't cover for 300 here. I think we stopped at 290 something. If you want to try it, you can try it. So I'm not going to be using 100. And don't forget our observation, the highest, the maximum we have in our observation is 300. So I'll be using 105 instead as the lower class limit of the first class. So starting from 105, sorry. Okay. Now you can start from 105 here and then add 21 rather than 22. So if you add 21 to 105, then you are going to have a range of values that are okay. You're going to have a class width of 21. So when you do 126 divided by, or rather 126 minus 105 plus 1, that will give you 22 actually. So you are going to need to add 21 to 105 rather than 22. So you add 21 to it. So if the class width had been maybe 10, you'd have needed to add 9 to 105. So you add the class width minus 1 to whatever you have as the upper class interval here, or upper class limit. So that's what I've done to get 126. Then when you have gotten the first class, then you just need to keep adding. This is 22. Don't forget, in order to get this one, we needed to add the class width here to 105, but minus 1, and then we'll minus 1. So that means that you are adding 21 to this. So don't forget about that, please. But now that we have the two, say 105 plus 22, so that will give us 27. Add 127 rather. So add 22 to 127, that will give you 149, and keep adding 22 until you get everything to the last class. Don't forget there are 9 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. So then to the second one, you do the same thing. Keep adding 22. When you add 22 here, you get 148. You add 22, you get 170. You add 22, and like that until you get to 302. And so when you have done that, you'll find out that you just have 9, as I said before, 9 classes. Now the class width is going to be 22 for all of them. When you do the upper class boundary minus the lower class boundary for each of the classes, or when you do upper class limit plus lower class limit plus 1, you're going to get 22. All right, so now the class mid-map will be obtained by adding the upper class limit plus the lower class, adding the upper class limit and the lower class limit. So when you add them up, divide by 2, you're going to be getting all of these for each of them. Now, so that's about that. That's how you get that. Now, having known that, I'm assuming now that these are the frequencies and that we have 150 at the end when you add everything. This one is just by way of explanation. I know I didn't give the data set, but just I'm assuming that we have we have 21 values that are from 105 to 126.